All right, so let me go back to March 24th, Tuesday. Take a look at these rules. Make sure you know these for your mastery test. Mastery test is on Thursday next week, so that's Thursday, April 2nd. So basic rules, kind of a shortcut for square root. You can also use power rule, exponential, logarithmic, power functions, constants, trig functions, inverse trig functions. Just notice the patterns between them to make memorizing them a little bit easier. So, in any case, we talked about those before. Do keep in mind there's two different notations for inverse trig functions. Inverse sign, written with the -1, just like inverse function, f to the -1, doesn't mean 1 over or reciprocal. It means the inverse function. Arc sign also means the same thing. Inverse sign, arc sign are the same. They both mean the input is a number between -1 and +1, and the output is an angle. So, in any case, make sure you know those rules. Here are some examples of the first half of the mastery test. Mastery test is 35 questions long. The first 25 are questions of this difficulty level. As you can see, kind of basically straight off the list that we're looking at, only with coefficients. These are each worth 2 points, so that's 50 points of the 100 points on the test. Again, these are basically straight off the sheet. Only thing is you'll see like actual power rule. Power functions are the ones that can hide in the most different forms. But look through here, you'll notice there are a few of these questions that are not varying. So a few of these are constant functions. They're all just written as y equals as opposed to f of x or something function notation form. But regardless, there's only some of them actually vary. And what we're looking for in all the mastery test questions are what's dy dx or y prime with respect to x, change in y with respect to changes in x. So if there isn't an x, notice your rate of change is going to be 0. So looking through here, here's one, number 8, y equals e squared. E is 2.7, so this is like, I don't know, y equals 8 something. Whatever e to the second power is approximately in decimal form. So this one is a constant. Looking through the rest of these, there's a couple more. This one, sine of e, e, still a constant. So this is sine of 2 point something or another. And so that's just a single number. The derivative here is 0. And there's one more right above it that I see. Natural log of 7, also a constant. Oh, here's one more. Pi to the 1.5. Pi and e and all these other symbols, just realize they're not x's. They are constants, 3.14 approximately. Natural log is a function name. E, 2.7 something. So we'd have to have another variable in order for this to have a non-zero derivative. So those four have 0 derivatives. Keep in mind something like this. Probably best practice to think of this in power function form. This would be the same as, not that its derivative is, but this is the same as x to the -2/3 power. So its derivative then would be, using power rule, -2/3 times x to 1 lower power, -5/3. Similarly, let's see, power functions, like I said, they hide the most. Here's this, which is a square root with a third power underneath, so that's a 3/2 power. Here, I wrote y, so y equals x to the 3/2 power. Therefore, the derivative y prime, or dy dx, is 3/2 x to the 1/2. For something like this, just don't estimate and use decimals. Y prime, I think you had some practice problems like this in your mastery practice online, but just leave pi as pi. Pi times x to the pi minus 1 power. Don't use like 2.14 or something like that. And of course, again, careful with power rule and negatives. Make sure you actually get a number that's 1 lower, so x to the -8th power. just some simple places that people make mistakes on these. Just might as well just kind of go through a couple more of these. Logarithms was base other than e. Natural log of x derivative would just be 1 over x. For something like this, we get an extra factor in the denominator besides the x. It's natural log of that base number. The common mistake that I've seen people make when in a hurry is to have something like 9 times the natural log of x. Just keep in mind that both with exponential and logarithmic functions that aren't base e, the extra factor is going to involve a natural log of a number. It's a constant factor that needs to be compensated for. In natural logs, it's in the denominator. And in exponential functions like this, it's not in the denominator. The derivative of this, so e to the x is its own derivative. 5 to the x is almost its own derivative. We're just off by a multiplied on factor of natural log of 5. That one I know we talked about in class before break. So these others, e to the x, that's the easiest one. Arctangent, arcsine, cotangent, cosecant. Just make sure you're good with your trig derivatives. Arctangent means the same as inverse tangent. If you like seeing it that way better, please write it that way. But the derivative is the same either way. Y prime, 1 over 1 plus x squared. That's just straight off the sheet. All right, so moving on to things that aren't just straight on the sheet. Take a look at this. So the idea with these longer problems, and you'll have a few longer problems, the remaining 10 questions on the test, I would say there are about 7 of them, 6 or 7, that are kind of a simple product rule, a simple quotient rule, a simple chain rule. And then there'll be 3 more that are more of this difficulty level, where there's a few different things to do. So looking at this, notice, okay, I have chain rule obviously because it's not just a simple something off my sheet, but I have a square root of something that's a whole other function. We're thinking about starting from substituting in something for x. I'd have to evaluate a bunch of things, multiply these together, add that. So I've got a product rule. I've got, well, addition is easy. And then take a square root of the whole thing. So there's a chain rule with a square root. So overall, this f of x is a square root function. It's a square root of something else. And if I want to find the derivative of this, I'm going to work on focusing on finding the derivative of this underneath part, because that's going to be the hard part. Because the square root of x is just 1 over 2 root x. So derivative of something like this, square root of g of x is 1 over 2 root g of x. But then chain rule says times the derivative of that inner function, the inner part of the composition. So in terms of, oh, I'm ready to write out f prime. This part I can write out right now. I'm assigning g of x to be that stuff underneath, the radicand. All we need to do, work-wise, is figure out what's the derivative of the stuff underneath. So I've got those 2 terms. And the first term is a product, which means I'm going to have to use product rule, but then there's just a sum. Finding the derivative of sine of x, easy enough. But I'm just finding the derivative of both halves of the sum. For the first half, I use product rule. So 7 to the x times the derivative of tangent of x, 7 to the x secant squared of x, plus, other way around, the derivative of 7 to the x and tangent's original form, multiplied together. So here's the derivative of 7 to the x and tangent as it originally was. And then outside these parentheses, here's all of product rule plus derivative of sine of x, cosine of x. So just putting the pieces together now, and this is something I might suggest you do on scratch paper during your mastery. Write this out instead of just trying to do it directly on the computer so that you don't go dizzy with parentheses and forget a factor or a term. Write out the general structure, write out the pieces, and then fill in the blanks. So now I'm ready to fill in g prime of x times 1 over 2 times fill in g of x. And again, doesn't matter if you write these 2 pieces in the other order, like 1 over 2 root g of x first, and then times g prime afterwards. Same thing. It looks ugly when it's put all together, but if you break it down and think about it piece by piece, it's not really all that bad. All right, let's look at one more like that. So we've got f of x equals some stuff in parentheses times some other stuff. So I've got x to the 3/4 minus 5x. If that were the whole thing, that would be simple. But that's all raised to the 9th power. So I've got a composition of that binomial sort of expression, I guess 2-term expression, not a whole number power, and a 9th power function. So I've got a 2-term expression raised to the 9th power, and then also multiplied onto e to a power. Well, and this e part isn't just e to the x, it's e to the, well, it's got a whole other function in its exponent. So I can see there's going to be chain rule with power rule, and there's going to be chain rule with our exponential function rule also. So overall though, last step order of operations wise, this is a product. Because if I were subbing in for x, I'd evaluate the 2 parts and then multiply them together. The 9th power part and the e part. So if I can think about working out the derivatives for each of the 2 pieces separately, that's what I need for product rule. Because product rule, I'm just calling them p and w instead of f and g, since I already have an f here. I need the derivative of 1 part times the original 2nd part plus other way around. And again, this is all addition and multiplication, so it doesn't matter what order I write these 2 parts in, what order I write those 2 parts multiplied in, or even if I write the sum done in the other order. But just don't multiply an expression times its own derivative. It's going to be one of the function factors, one of the factors of the function times the other factor's derivative, and then vice versa. So this first term here, its derivative would involve chain rule. So you can work outside to in or inside to out. This is the inside to out part, so the derivative of what's inside the parentheses times the derivative of the outer with respect to the inner. So leaving the inner part intact, just like the derivative of x to the 9th is 9x to the 8th. We don't change the x to something else there. We're not going to change this inner part to something else either. Whatever expression was to the 9th power, in the derivative, that will be to the 8th power. There's going to be an extra factor tagged on that's the derivative of that inside part. So this is all power rule, both inside and outside. The derivative of e to the 6th square root of x power. If you want to think of it as 6x to the 1/2, you can, or if you just remember your derivative rule for square roots, that can also be helpful. But the derivative of that exponent, if you don't simplify, looks like this. You could obviously simplify that pretty easily to 3 over root x. But in any case, 6 over 2 root x. This 6 is a coefficient, or 6 times 1 over 2 root x times itself, times e to the 6th root x power, e to the 6th root x power. So now I've got the original first part, the original second part, the derivative of the first part, the derivative of the second part. Now I can piece them together with chain rule, and it's going to look really long and ugly, but those are just all the separate parts. So I've just used brackets here for emphasis. Those are they work the same as parentheses, but make sure that you do have the entire pieces multiplied together. If I were to just use the dots and not have parentheses or brackets here, in this particular case it would be okay because each of the individual pieces is a single term expression. There's no addition or subtraction outside of parentheses. But just general practice to make sure you don't do this in other cases. I need the whole derivative multiplied by this whole original part. And again, this whole original part times this whole derivative. All right, so let's talk about using derivatives to actually do something instead of just finding derivatives. And trying to remember if we actually talked about this or if this was just an example in your book. But a volume of concrete in cubic meters poured during construction of a skyscraper is given by V of x equals 30 times the quantity 1 minus e to the negative x 15th power. X is an amount of time in seconds. And again, V of x, the output is volume of concrete in cubic meters. So this is an amount function. It's something that tells us how much of something we have, how much concrete we have. So let's think about, how do I find the rate at which concrete's being poured? All right, well, the rate at which concrete's being poured in cubic meters per second, this function gives me, well, based on seconds, it tells me cubic meters. So this would precisely be asking for the derivative or the rate of change of function v. So I can call it r sub v of x. I could call it v prime of x. Either of those are perfectly fine. Oops, sorry, as usual, just this causing problems. So the rate of change of this, r sub v of x, or v prime of x, whatever you pick your favorite notation, dv of x dx. I want to know the derivative of this. So I've got a coefficient of 30, and then I've got this expression in parentheses. So this is just a constant multiple. And I can work on simplifying this later, but finding the derivative of the two terms inside. I've got derivative of 1 minus the derivative of e to the negative x over 15. Well, e to the negative x over 15, we were just talking about stuff like this, is in its own derivative. I just then have to multiply by the derivative of that exponent. Keep in mind that negative x over 15 means the same as negative 1/15 x. It's a linear exponent. Derivative is its coefficient, that slope, negative 1/15. So here's an unsimplified version of the rate of change of the volume, the rate at which the concrete's being poured. Now, for the purposes of mastery test, no, you don't need to simplify. For the purposes of, I'm going to need to do something with this, you might want to clean it up a little bit, especially when it's not too hard. So 0 minus, obviously I don't have to write the 0. And then I've got a negative, or a subtraction, multiplied by a negative. So this negative e to the negative x 15ths times negative 1 over 15 is going to end up being positives. And then, well, just instead of writing 30 times e to the negative x over 15 times 1/15, the 30 and the 1/15, I can just write that as a 2. So simplified version of this, whether I call it r sub v of x or v prime of x, I can maybe write this as just 2, e to the negative x over 15. So that gives me the rate at which concrete's being poured, where x is a number of seconds, and the output of this rate function is in cubic meters per second. Now, going on, let's do something else with this. At 10 seconds past the start of a pour, a light signal is turned on. Use that rate function to describe an open form function for L of x, the volume poured after the light turns on. So it's not just this, the volume poured after the light turns on. So let's just start from here. This is something that we did before your first test, or we started to. At 10 seconds after the light turns on, I want to know what accumulates past time 10 until any time x. So the amount after the light turns on that accumulates, well, it's accumulating starting at time 10 up through any time I want, and it's accumulating at this rate. So 2e to the, I'm just going to switch my variables, negative t over 15 dt. This is my mdx sort of expression. The rate, each rate times a little bit of time to measure an accumulation. So this doesn't have any starting amount, it's just wherever I start at times 10. This is how much accumulates past time 10 and until time x. So if I wanted to relate, it should be, V of x and L of x must be related, right? Because V of x gives me the total amount of concrete since we started pouring, that is since time 0. And L of x is just how much was poured since time 10. So the difference between them should just be, in words, the amount of concrete that was poured in the first 10 seconds. But I know a computation for this already. The amount of concrete that was poured in the first 10 seconds, V of x helps me describe the amount of concrete that's poured since the start. So V of 10 would be the amount poured in the first 10 seconds, between time 0 and time 10. You could also write V of 10 minus V of 0, but V of 0 is actually 0, and you can even see that since we have this function written up here. But I could say that V of x then equals, or minus L of x equals 10, or not 10, V of 10. Or we could write this in lots of other formations. I could say V of x equals V of 10 plus L of x. And this formation, the reason I picked that one, that looks like our fundamental theorem of calculus if you use this version of L of x. The accumulation at any time x, I can define based on what I start with and then what accumulates afterward. So I can say, okay, so I start at 10, and then whatever I accumulate afterwards from 10 through x at this rate to e to the negative t/15ths dt. This is one of infinitely many ways I can express v of x, because there's no reason I had to use 10. I could have used any number there. Just this particular question asked us about this 10 seconds since the start of the pour. But this would be true for any value 0 or larger in order to see what happens. And in fact, that x value, using 10 here doesn't exclude us from using x up here smaller than 10. It just would seem a weird way to do that in this context, but it actually would compute out right, because what would end up happening is it ends up subtracting the changes that happened between 10 and this earlier time if you were to do a computation. Because if you remember, the other part of the fundamental theorem of calculus that we talked about, I'm just going to jot it here where there's some space, if this will let me. If I want to find an accumulation between point A and point B, all I have to know is the original function and compare its starting and ending values. And when we wrote this, we wrote f of b minus f of a, like final minus initial, but it doesn't actually matter if this is some sort of time-related thing, if this is an earlier time or a later time. This expression means to do this, regardless of the relative sizes of a and b. So even if I had in this expression down here 10 through 3, I'd do f of 3 minus f of 10, and that would give me some sort of negative result, which would then subtract off from v of 10 what happened between time 3 and 10 to get me back the result that I wanted, v of 3, as an example. All right, so let's go on thinking about something else to do with derivative rules. So our rocket basketball, I know we talked about this in class for a few different days, The upward velocity in meters per second was given by v of t equals t to the 1.3 power at t seconds after launch. And this wasn't part of what we did before, but let's say it was launched from a height of 6 meters above the ground. We were just working on doing general accumulation when we did this before. And we talked about our summation and piecewise functions and all that fun stuff. So if I want to write an open form function giving its exact height, let's not use summations and piecewise functions with constant rates for long periods of time. Let's just talk about an exact value of the height at t seconds after launch. Well, my height's going to accumulate due to this. Ooh. So I can think about accumulating from launch until t seconds later. I do want to have this be h of t. So I'm going to use t at the top there, which means I'm not going to use t inside the integral. But my rate, this velocity, that's a rate of change of my height. I'll call it w to the 1.3 power, dw. And so this tells me the accumulated height from time 0 up until any time t. I just have to add on my initial height. So this is my y initial plus mdx structure. Starting height plus what happened due to the rate of change. So this will work to give us h of t. So the second question that I popped up here, what do you know about function h of t? Some values, a type of function. Can you recreate a closed form h of t that has all these qualities? Meaning, what is this the derivative of? We've done derivatives that end up with results that look kind of like that before. If it was supposed to look like this precisely, I'd say, well, let's see, h of t would have to be something that involves t to a higher power, one higher in fact, so that if I do power rule, this 2.3 in the exponent would become a 1.3. Now, a couple other details. If I don't put a coefficient on this t, if I were to take the derivative of this, as it is right now, I just get 2.3 times t to the 1.3. So to counteract that coefficient, there. Now, if I take the derivative of this, I get precisely 1 t to the 1.3 power. Now, I left a blank here, and I left a blank here because, well, if I just use h of t equals this at t equals 0, this would have a value of 0. I want it to have a value of 6. So, well, look at this right now. I want h of 0 to come out to be 6. So if this part's going to go away, I better add on a 6 here, which we'll talk about another way to do this, but my starting height plus what happens afterward. This has this second property here. This is kind of the equivalent of, what we're doing here is the calculus equivalent of, I gave you the slope and the y-intercept. Write the equation of the line. Right? So if you remember from algebra, if I said, oh, the slope is 14 and the vertical intercept is 6, you'd say, oh yeah, y equals 14x plus 6. And it's just an easy pop it in there. Now, what's not quite as easy is if it wasn't a vertical intercept, but there's another way to deal with that, just like there is with lines. If I said, oh, the slope is 14, and it goes through the point 5, 9. Not true with this, nor is the slope 14. But we talked about that even earlier in this class, just as a way to put together those piecewise functions. We'd say y equals, well, y initial plus m dx. 14 times however far x has gone past a value of 5. So you don't have to do it this way. We can think about this instead, y initial plus m dx. So as long as you can come up with any function that has this as its rate of change, if you know how to express the accumulation, you're set to go. So let's look at one other question part here. Suppose I wanted to write an expression that gives the rocket's change in height from time 4 to time 5.6 seconds. I want to know what expression with function notation would be equivalent to that. Well, the rocket's change in height from 4 to 5.6 seconds, there's a few different ways we could write that now that we've written all this stuff, but hey, I wrote a function h for the rocket's height, h of 5.6 minus h of 4. But I also know I could write that even if I didn't know this function h in closed form like that, I could also use this format. The change in the rocket's height doesn't depend on what height it was at time 0. It's just going to be the accumulation between time 4 and time 5.6. And you can use really, in this case, whatever letter you want inside. I could use T if I wanted to. Oops, sorry, didn't click on my eraser properly. But I'll just use W. I just won't use a triple U. W to the 1.3 dW. This would express the rocket's changed height between time 4 and time 5.6 seconds after launch. So here's not using function notation, but it is kind of cool. And here is with function notation, our h. We can talk about it that way. All right, so let me clear this stuff off. Here's one other question. We talked about this, we'll talk about this one on Thursday. So just think about this in advance of Thursday's lesson. If you're watching this later, go back and watch the beginning of Thursday's lesson. We'll talk about this. But same sort of thing with a general function for rate instead of a specific context with launching and rocket height. So we've got an initial value and we've got a rate of change. All right, so enough of this. Let me get out of Keynote here. And let's take a look at something else for a little bit. So I'm going to set this in motion, but take a look at the graph on the right as x increases. This is a graph of f. I suppose I can notate that. So this is y equals f of x. It's being graphed here. And over here we can see values of r sub f of x. The rate of r sub f of x is the derivative with respect to x of this function f. And so this is so that I can have it as the slider. This is our x value. As x is increasing, I can see what happens to my rate values. So I'm going to pause this in a couple places. But notice during the first portion of this, I've got positive rate values, positive rate values. That shouldn't be a surprise. Look, my function f is the f of x, the y values are increasing as x increases. I've got positive derivative values corresponding to this uphill motion on the graph. Now as I go a little bit farther, and see, well, it's still a positive rate value, positive derivative value, but it's much smaller. And as I go right close to the top of this hill, I can see it changes to hardly positive at all. And then I don't even know if I can stop it at anything. So here's positive 0.12, negative 0.05. Right around the top of the hill, I've got this. It changes over from positive to negative. And then I've got negative values that are becoming more negative. Negative 2, negative 3. Let me put this back to playing mode again. Negative 4, negative 5, negative 6. Oh, and then it pauses and goes back. Negative 5, negative 4, and so on. So that when we reach the bottom of this hill here in the function, visually speaking, I can see right around there this derivative is very near 0. If I nudge this a little bit, I might be able to get a little bit closer. Just pixel width is a little small here. That's essentially 0. And then it becomes positive again. So this is smoothly changing from positive to positive again as we go from left to right. So look at this function. And I have the dotted lines here so you can more easily follow up and down. Look at this function and think about over what intervals f of x is decreasing. And then also think, where's the rate of change decreasing? I'm going to scoot this back down so you can see the rate function values. So those are two different questions. Where's the accumulation? Where's f of x decreasing? Versus where's the rate of change, r sub f of x, decreasing? And if you want to add on a couple more questions, also list where each of them is increasing. So if you're watching this after the fact, pause, and let's talk about these. I'm going to pause the animation here, so it's not moving all the time. But just thinking about where's f of x decreasing? Well, where it is right now, that's definitely decreasing. When I'm going downhill, visually speaking, that's this accumulation decreasing. So just looking at this best guess-wise, let's say around boundary values are the top of the hill and the bottom of the hill. So between those two blue dots that I just put on here, f is decreasing. If I wanted to describe that interval of x, and just now I know I can use this and scroll around, get more precise, but really I'd want to solve for those locations, those boundary values. But where f is decreasing is about negative 1.75, I'd say, through 1. So negative 1.75 through positive 1. I'm using open intervals because if I'm declaring that this is the point, negative 1.75 comma something, at that point, I'm not really wanting to declare f decreasing, nor is it at this. At those 2 points, that's where it's changing direction, changing from increasing to decreasing at this point. Or in this neighborhood, the rate of change is essentially 0, or essentially f is unchanging within that little circle. The output values are essentially unchanging. So between is where they're decreasing. If I wanted to say where is it increasing, well, it'd be out here. So out past x equals 1, 1 through infinity, and down below negative 1.75. So negative infinity through 1.75. So let me just note that, as long as we're talking about it. Let me change colors though. So increasing on negative infinity through 1.75, and also from 1 through infinity. And the only points in f of x's domain then that aren't included are negative 1.75 and positive 1, because at those points f is neither increasing nor decreasing, it's changing. It's changing from one to the other, or I'd say that the values approximately, or it's in terms of f is approximately constant at those points. Now, talking about the derivative and where the derivative is decreasing. I'm going to erase this because those points aren't going to be what's important. So thinking about this, I know that the derivative was positive, positive, positive all along here. But let me put this back to play again. Right now, is the derivative increasing or decreasing? I've got 23.4 for a derivative, 20.4, 17, 13.4. That's not increasing. It's positive, but they're positive numbers that are getting smaller. So right now in this section, this whole left portion so far, The derivative is, although positive, it's decreasing the whole way. So think about how far does it continue decreasing. Watch these numbers get smaller and smaller and smaller. 5, 4, 1, 0, -1, -2, -3. That's still decreasing, right? It doesn't decrease much farther, though. In fact, if you're watching that, as x increased at a constant rate, this kind of seemed like it was stuck for a little bit. It went from -5 to -6 to -6.33, I think was the lowest, and then it started going back up again. So right around if you see as I'm dragging this right in this vicinity, that derivative stayed at -6.33. Now it's changing in later decimal places, but just to not be dizzying, right around negative x equals -0.38, this rate hits the lowest value it's going to hit. So it decreased from positive 30s all the way down to -6.33. And here, is where the derivative stops decreasing and then starts increasing again, going to negative numbers that are closer to 0, up towards 0, and then into the positives. And then as you can see, this becomes a more and more and more positive derivative as I continue to go to the right. So the derivative is always increasing past this point. So up to about, this was, oops, -0.38, I believe was the number that showed on there. To the left of that, r sub f of x is decreasing. Goes from a very high positive to a lower positive to 0 to negative to more negative until we get to here. That's a decreasing sequence of values. So let me put this back in blue, the blue answering the actual questions. So where is it decreasing? From -infinity up through -0.38. After that, the derivative is increasing, opening this up to a different shape. And if you can see this spot right here is kind of, with respect to this graph, it's kind of almost a symmetry point. A point symmetry, not a folded symmetry. But what this graph is doing on the left is kind of the opposite of what this is doing on the right. It's because it's a third degree polynomial. But in any case, this function's derivative that we're looking at a picture of, f of x is what this red curve is. F of x is increasing, then decreasing, then increasing. But its derivative is decreasing and then changes to increasing. So if I want to write that, let me just change. It's increasing. Which wasn't the question that was asked, but increases from -0.38 onward for the rest of the graph. So these are different boundaries. When we're talking about the first derivative, the boundaries between, and looking at a graph of f of x, accumulation. When I'm looking for boundaries between where f of x is increasing versus decreasing, those boundaries were the tops and the bottoms of these hills here, visually speaking. This is called a local minimum, meaning that it's the bottom of the hill. The points around it are higher. It doesn't mean that there aren't higher or there aren't lower points elsewhere, like these are certainly lower. This is just lower than the points on either side of it. Or if I were to draw a circle around it, it's the lowest spot in its neighborhood. Similarly, and let me get this writing out of the way, this top of the hill is called a local maximum for the same sorts of reasons. And we'll get more into this in Thursday's lecture, but this is called a local maximum. And it indicates this place where the accumulation changes from increasing to decreasing. This change is a change from decreasing to increasing. This point in the middle is not about a change in the accumulation. It's about a change in the rate of change. Visually speaking, the curvature of the graph changes there. This is like, hilltop, hill bottom. This is what's called curved down or concave down. This is curved up or concave up. At this point, this is the changeover for where I describe the curvature as curving down to curving upward. And it's called an inflection point, or just an inflection. And they don't have to be on a weird angle. They could be horizontal or vertical or at any angle. If you can imagine, I could rotate this graph. Wouldn't make it a function anymore necessarily, but if you can imagine rotating this graph, inflection points can occur at any angle. It's just relative to the curvature around it, it indicates that it's changing. All right, so let's go on and take a look at those concepts a little bit more and the idea of the rate of change decreasing versus increasing and what that all means, just briefly, and then we'll be finished with this. Clear that off. I've got another keynote for you. Someplace. All right, so if I'm looking at how a rate of change function is changing as x increases or as x varies, what happens to my rate of change? Realize that we can think of that as the derivative of the rate of change. Just when we're talking about how y changes as x varies, or how the accumulation changes, does it increase or decrease, as that's a derivative. This is the derivative of this rate of change, or derivative of a derivative. So it's called the second derivative, so you don't get dizzy saying it. So if we're talking about how the rate function is changing, we're talking about a second derivative of accumulation. So there's a few other notations for this. They all involve 2 in some way or another. So the dy dx notation that we use for derivatives, this is the second derivative equivalent. The prime notation, this is the second derivative equivalent. These are pretty easy. Usually this is set as y double prime or f double prime of x, or just second derivative. It's not usually read as prime prime. But let's talk about these. This notation is a little bit more mysterious. It's always messier, this slope style notation, change in y over change in x. But I want to explain why the 2's are in different spots. You can maybe see because of this. So if my first derivative is called dy over dx, which also comes from take a derivative of, kind of the command form of y. So in this notation, take a derivative with respect to x of y, or of f of x, whichever you want to call it. I can write it in a single fraction like that, and it kind of looks like we're doing multiplication, like put this y over 1, and then it'll end up on the top. So it's really just notation. It's not multiplication, nor is this in reality division. We had to do trickery to get the division to simplify into something nice, letting the h part become approximately 0. But imagine if I want to take a derivative of this. So if I were to play the same game, it looks like multiplication. Well, notice we have dy on the top, well, 2 d's and a y, and on the bottom dx and dx. Oh, that's dx squared. It's not really multiplication, so don't think of this as multiplication, but if you can see, that's kind of where the 2's end up where they do. Notice there's no parentheses because it isn't actually multiplication, but I just wanted to explain the kind of the origins of this notation with the 2's in bizarre spots like that. So in any case, if you see these, if it had a 3, that would mean the derivative of the derivative of a derivative, which has more limited applications or uses, but certainly is useful. One thing to keep in mind, though, there are no new derivative rules for taking a derivative of a derivative. Same rules as before. If you want to find a formula, we know all those from mastery test studying, but these are notations for second derivative. Now, meaning of second derivative, again, if I have a function's output, an accumulation function that was increasing, we'd say its rate of change is positive. But any function that's increasing, its rate of change would then be called positive. Whether that's, don't worry about that. Whether it's a regular accumulation function or even a derivative. If a function's output is decreasing, whether that function is an accumulation or already a rate, I can say that the rate of change of this, whatever it is going to be negative. So all this is just a kind of silly greater than 0, less than 0 division process. Don't worry about that. Final minus initial, if you have something decreasing, is going to be negative, and when you do division, you get a negative result. But the main idea here, just briefly then, is that if I have values of a function increasing, its derivative is positive. If I have value of a function decreasing on an interval, then the values of the derivative there are negative. And this is for any function and its derivative, whether I have an accumulation function and its rate of change, like height and velocity, or something that's already a rate function and how that rate is changing, like velocity and acceleration. Same principles of relationship hold about the patterns between increasing and decreasing for the main function we're talking about, and positive versus negative for the rate of change of that function. And the only other part that I wanted to do to link all this together was just going all the way from like an accumulation to a second derivative. And that's what we talked about visually speaking with GC. If I have the second derivative positive, that means that the first derivative is increasing. So going all the way back to regular f of x, sorry, I skipped past that animation because I touched instead of just circled. All right, here. So if my second derivative is positive, my first derivative is increasing, whether that means from a negative to something less negative, to something 0 to positive. But if you can imagine, negative to 0 to positive first derivatives would be this negative to 0 to positive, down a hill and back up sort of pattern. But any part of that also would indicate that we're on a portion of a curve, and it doesn't have to be this whole thing, but just a portion of a curve that is curving upward if that derivative is, if the first derivative is increasing, or the second derivative thus is positive. In the other order, if I have a second derivative that is negative, that means that my first derivative is decreasing. So that could be a positive to something less positive first derivative, or positive to 0, 0 to negative, or the whole process. But that would then indicate then that the function f would be some portion of, at least, a turned down, kind of a frown face shape. So you can go all the way from accumulation to describing the derivative to describing the second derivative. I can talk about a function, whether it's increasing or decreasing, its derivative would be correspondingly positive or negative, but I can also talk about whether the derivative is increasing or decreasing by looking at the shape, which would indicate the signs of the second derivative. But that's it for this, and I will see you next time.